Okay, so welcome to Gary Rick Services HVAC Journeyman class. Today we're talking about water, evaporating, cooling, and an introduction to refrigeration. Sean, you can get the video of this if you want later.
Oh, that's right.
I mean,
Just send it to me.
just look around.
Automatically.
There's cameras here. Okay.
You get an extra one.
All right. So you can flip it to the computer. All right. So everything that I'm going to talk about is going to be up there. All right. Water. What is it? Here, hold this water molecule.
Hydrogen and oxygen.
Hold this water molecule right here.
That's what H2O.
That's what it feels like.
Plastic. Feels like a Mickey Mouse head.
It's this. Water is made up of 3 atoms, 1 oxygen and 2 hydrogen. Hydrogen are smaller. Looks like Mickey Mouse's head. Hey, Greg, don't be breaking up my molecules. You know what happens when you do that, right?
What did that create?
That created an explosion. That's an unstable atom. All right. Experiment 1 here. I'll put a few drops of water down on the table here so you can see them. Right now, the atoms, the molecules, are evaporating off of this water, and it's happening very slowly. Okay? In a drop of water, there are 1 sextillion H2O molecules. That's a 1 with 21 zeros behind it. So 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. It's a lot. To put that into perspective, the scientists estimate that there are 7.5 sextillion grains of sand on Earth. Tiny. Cohesion. That's how water sticks together. Okay? Hydrogen bonds is the weak electrostatic bond between molecules. Like a magnet, the water molecule is polar with a positive and negative side. Hydrogens are positive and oxygen is negative. Because opposites attract, it makes the water molecule stick together. Molecules that stay close together are called cohesive. Look at this. That's how magnets work.
What does that have to do with water?
Water molecules are cohesive. They have a positive magnetic charge and a negative magnetic charge, which makes them stick together. If it didn't, the water molecules would just fall apart and they'd become steam instantly.
Is that what Rain-X does? Is that
What's
why it
that?
just falls?
Rain-X, I'll get to Rain-X. Evaporation, how water cools. So let's see. Add some heat to this pot of water, and hopefully, Greg, did you bring on your goggles today? I wish you would have. Okay, so I brought out, added some heat to the pot of water, and I've got the ice there. H2 molecules in the ice form have low kinetic energy. H2O molecules in the water form have medium kinetic energy. H2O molecules in vapor form are going to have high kinetic energy. In liquid, each water molecule has different kinetic energy. All these molecules are moving around. But the molecules on the surface have a lot more kinetic energy. And when molecules are compacted close together, they're bouncing around and bumping into each other. Ouch. Each different H2O molecule will have a different kinetic energy and temperature. Water molecules water temperature is the average kinetic energy of all the drops in the mass. So this one's going to have maybe a little bit more kinetic energy than this one, but they're all going to be moving around. Okay? And if this one's moving faster than this one, and this one, and this one, and they all have different kinetic energy, then the temperature is going to be the average of the mass. Okay? Equilibrium. That's the state in which opposite forces are influenced or balanced. Liquid water H2O molecules are evaporating to reach saturation pressure of the water in the gas phase and will continue until the air is saturated. So the air out here, the water in there, the water is going to be evaporating when there's a differential between pressure and temperature. This liberation happens very slowly but will increase as you add more kinetic energy, like airflow across it or by adding heat. Evaporating liquid without boiling. H2O molecules on the surface of the water have higher kinetic energy than the molecules below. They must break free of their hydrogen bonds from the other H2O molecules to overcome the pressure in the atmosphere and could become water vapor. Yeah, Greg?
Can you keep the slides on the screen
Ask Stephanie.
permanently?
Yes. Is that okay, Steph?
Not for your drop of water.
Huh? Oh yeah. No, not permanently.
Or do a picture-in-picture?
Here, will you zoom in on this water real quick?
I can picture for you.
Okay. So we're going to zoom in on this water. And you'll see that when I turn on the fan here, look, the water is moving. We're adding kinetic energy right now to that water, and we're making it evaporate much quicker. When I move air across a drop of water, the molecules on the surface gain kinetic energy and the water will evaporate much quicker. If you look carefully at the drops of water, you'll notice that they are moving. See them moving? Okay, you can come back out, Steph. The molecules with the highest kinetic energy break free. Average kinetic energy of the mass lowers. Average temperature drops, causing a cooling effect. This is how evaporation cooling works. So the mass is getting smaller and smaller. Let me see your H2O molecule. I'm going to show you guys something. Are you ready for this? That's how it's happening. Right there. They're breaking free and getting blown off into space and time. Actually, just the air. Okay? This right here is a cyclometer. Cyclometer. Okay? This is going to tell us what our humidity is, what our dry bulb is, and what our wet bulb is. Right now it's set on wet bulb. In here we have a 54-degree wet bulb. Okay? A cyclometer is an instrument that measures temperature and humidity to calculate wet bulb. This right here is a thermometer. And it's working good. It's 72 degrees in here. So 73 degrees in here. So 73 minus 53 is what? 20 degrees. That is the delta T. I'm going to wrap this piece of cloth around here. And right now, with my hands on it, the thermometer is reading 76 degrees. It's important to know your starting point and your ending point. So if I dip this sock and saturate it fully in water and put it in front of the fan, ooh, can you see that on the thermometer? Is that clear? Okay. You'll notice that the temperature is going to start dropping on that thermometer. That's because the mass of the water is starting to evaporate that's soaked into that cloth. This is the wet bulb. This is called a wet bulb. And that measures the cooling effect of water evaporating and can be determined by a thermostat, a thermometer with a wet cloth called a sock with ambient air moving across it, or a cyclometer. Psychrometer. Okay? The delta T is the difference, is a differential measurement of two temperatures starting and ending points. So right now, we started at like 76 and we're still dropping. This is reading 53 and this is reading 54. They'll be pretty close by the time that's done dropping, maybe within a degree or two. Natural evaporation stops. Evaporation will continue until the air is fully saturated. Once this happens, the dry bulb temperature and the wet bulb temperature will be the same. Okay? And we will have equilibrium, complete equilibrium, or full equilibrium, meaning that there's no more differential there. The water can't evaporate anymore, naturally. Here in northern Utah, evaporative cooling stops the end of the end of July and early August. That's why people start calling and say, my evaporator cooler is not working anymore. And then we say, you know, the wet bulb and the dry bulb are the same temperature, and that's why. However, we can force water to evaporate after equilibrium. "51 degrees. So we had like a 24 degree temperature delta T. And that's pretty good, because that's what you can expect out of a cooler with fully saturated pads when there's that big of a differential. So evaporative coolers work pretty well until that point where the wet bulb starts to come up to the dry bulb temperature.
There's just nothing you can do at that point.
There's nothing you can do. You can add an air conditioner. What would be better than an evaporative cooler? A whole house fan would be better than an evaporative cooler, because number one, you're cooling down your house in the middle of the night without that wet humidity coming into your home.
Is there a temperature range where swamp coolers are kind of ineffective too?
Is there a temperature range where swamp coolers are ineffective?
Yeah.
Swamp coolers and evaporative coolers are the same thing. It's the same thing. Evaporative coolers and swamp coolers. We used to call them swamp coolers when we're rednecks, and we call them evaporative coolers when we're high class. Okay. Superheating. We know what superheating is when we're refrigeration technicians. It's when the heat of a liquid under pressure is above its boiling point without vaporization. So right now, the pressure of the water is increasing in this pot, right? And it's starting to boil. It's not boiling very rapidly yet. I'm going to turn up the heat a little bit just so we can get a little bit of a boil. You can see the droplets are, oh, now it's starting to go. So it's slowly evaporating now. I'm going to turn down the heat a little bit now, just so we don't have too much. Adding kinetic energy to a pot of water, adding kinetic energy. If we take a pot of water and add heat, increasing the temperature to 212 degrees or more, the water will start to boil and remove heat from the heat source. This is called superheating. So the heat source is here, right? It's boiling. The heat is being removed and turned into steam right here. Okay? If I put a lid on this pot of water, you'll notice that there's steam forming on the top of that lid. It's going to start condensing quickly because the lid is colder. So it's dropping that temperature below the superheat, 212 degrees, and we call this subcooling, a liquid existing at a temperature below its boiling point. If we add a glass lid to a pot, you can see water vapor is condensing back into water on the lid and draining back into the pan. That's because the water is cooling or subcooling, turning back into a liquid and removing the heat into the air. So right now we're removing the heat into the air. You can see it's really starting to condensate really good on the top of that lid. Turn up the heat just a little bit more, just so we can see some outgassing. So if I turn up the heat too much, then we're going to have outgassing out of this system, which means that the steam is going to be coming out of the lid, or it's going to be pushing the lid. So we're building the pressure in this pot up right now. And pretty soon, oh, I can see a little bit of steam there, but we're going to wait until it's really going. And then we're going to add some ice to it to cool it down. So you can see that if we're adding load to it, like ice, then it's going to continue, it's going to reduce, it's going to increase that condensing pretty quick. Can you see the steam coming out on the video yet? No? Turn this up a little bit more. I'll turn it down a little bit.
Ice is already starting to melt.
It's really condensating now. You can see on the top it's continuing to condensate, but at some point it's going to overcome the pressure of the lid sitting down on this pot. The pressure of the gravity is going to be overcome by the pressure of the evaporation, and we're going to start seeing much more steam. But then as I add the ice, we're going to see that steam. Can you see the steam yet?
Yep.
Go right down on the... Okay, so now you see the steam. I'm going to add this ice to it. Well, I'm going to try to. I did it with snow the other day. And it worked pretty good. Yeah, so now you're seeing the steam decrease and decrease and decrease. All right, so the refrigeration cycle. Now that we lowered the temperature on the lid, the gap with ice, the outgassing of steam is lower. This is a closed circuit refrigeration circuit. You can see the cycle between the boiling water in the pan removes heat from the heat source, and the condensing water is heat that is absorbed from the lid to the air and ice. In refrigeration, we call the pan an evaporator because that's where it's superheating, heating up beyond its boiling point. So superheating, taking the heat, the energy that's there, and moving it into steam. And we call the lid a condenser because that's where the water is cooling back into a liquid or subcooling. Natural refrigerant is water. R1718 or H2O. ASHRAE classification is A1, low toxicity and no flame propagation. That just means that it's a safe refrigerant. Now, we will get into the ASHRAE classifications later on. Boiling, superheating is heating it up beyond a point of 212 degrees. Condensing, subcooling is a point between 212 and negative 32 degrees. 32 degrees. Water is the oldest refrigerant known to man. It's environmentally friendly, non-toxic, can be consumed with health benefits. There's no ODP, ozone depletion potential. That's ozone, that's a chemical that would make the hole in the ozone bigger. There's no GWP, global warming potential. Greenhouse gases that make the earth warmer. It's the only natural substance on earth found in all three common states of matter: ice, liquid, and gas. And I'm finished. The end.
So what's his face actually called?
ASHRAE? What is it?
No. I said, what's his face actually calling? Or did he already stop?
What is what calling?
No, Mike 2.
Oh, yeah, Mike 2 said that he's not coming into work. Tomorrow, we're just going to have a continuation of refrigerant with our course study. We're going to be going over these two books right here. These are pretty good books. Unfortunately, due to copyright issues, we won't be reading out of them, but we will be doing all the experiments in here, talking about them. So you guys will have to read it in the evenings, maybe spend 10 minutes a night and read what the next day stuff is. What's that?
Said they copyrighted something?
Oh yeah.
No books
You can't read right out of a book.
Oh yeah.
That's basically reading out of somebody else's book. I can read parts of it, I think. I don't know exactly. How does the copyright rule work? I don't know exactly.
You can't share the material.
Yeah, so I can share the covers of it.
You can read it.
I might be able to share like the refrigeration cycle out of it, the picture, but I
You
can't
can-
just read
you
it to
can
you
read
guys.
it. You can read it. You can't show the book and distribute it.
Well, people just have to buy the book.
But you can read it.
So I recommend everybody buys this book and this workbook.
I have one somewhere.
I just don't want to take somebody else's work. Refrigeration is a universally known thing. So he wrote it out of universally known structure, right? That's fine, and he wrote a good book. Craig Migliaccio. I had to subcategorize his last name so I could read it and pronounce it. But I think he did a fine job with this book. I've read it like 4 times now.
It's good.
It helps me. It can help you. All right. Today we're starting a 2-system installation. And we need to get over there. It was at 7:53. All right. So that was good. Tomorrow, Steph, will you share these slides with everybody so they can review them tonight? Tomorrow we're going to have a little test again on it. I'm going to add a couple more questions to it. Stephanie's going to add some trickery.